Okay, hello, how's everyone doing? That is about the most enthusiastic response I've ever heard, ever. What is in these bags of food? I'm going to find out in a bit. Right. So, I'm going to talk a little bit about a couple of my favorite things. One of them is ancient Greece, because I flipping love ancient Greece. And the other is maths, because I also love maths, because as I'm always telling my daughters, maths is cool. And machine learning is basically maths. So, here we go. I'm going to have a go, because I am learning Greek. I think that is said, haspazomai, probably, which means hello. So, a little bit about me. If anyone is interested, I am the guy what wrote this book. If anyone wishes to scan this URL, which was provided to me by O'Reilly, I believe it will give you a month free on their platform. Feel free. If it does not work, have a word with me, and I shall speak to O'Reilly and get them to reactivate it again. Be warned, it is a very silly book, because I wrote it, and that's the way I write. Also, I was writing it mostly between the hours of midnight and 3 a.m. because I have both a wife and children, and that was the only time I had. So I was firing on pure, random, tired, weird energy the whole time. Okay, I am soon also to be the host or co-host of this podcast, which is coming up soon. One of the others is over there. Yep, there we go. Hello, Jeff. We are going to be, each episode, we're going to be talking about films which are about tech. So look out for things like Lawnmower Man and The Terminator, and someday I will get them to talk about my very favorite tech film, The Net. I love that film unobjectively. So what is machine learning? So for clarity, AI is a big old thing. A subset of AI is machine learning. Not all AI is machine learning, but all machine learning is AI. There is also a subset of machine learning called deep learning. This is outside the scope of this talk. But first I want to talk about a big old pile of stones. This is a philosophical problem which goes all the way back to ancient Greece. There is even an ancient Greek name for it. This is called the Sorites problem. So it goes something like this. So imagine that I'm building myself a big pile of rocks, or put myself a big rock on my big pile of rocks, which is only a single rock, and I will say, is this now a big pile of rocks? To which you will say, no, it is a rock. Fine, okay. I'll put another rock on my big pile of... Is it now a big pile of rocks? Well, no, it's a very small pile of rocks. Okay, and so on, and so on, and so on. Now, eventually, I'm going to put enough rocks on my big pile of rocks that you're going to say, yes, that is now a big pile of rocks. Wonderful, I'll take one off. Is it not anymore? That is the problem of fuzzy definitions. What is a big pile of rocks? You cannot say it's 7. It's not the way it works. Some things can't be defined quite so clearly and precisely. Some things have fuzzy definitions, where it's kind of obvious if you squint at it a bit, but it's really hard to just make a literal if statement that will cover it. And that is the problem that machine learning is attempting to solve. We're trying to come up with fuzzy answers to fuzzy problems in an attempt to say what stuff is, because that is really hard. So first off, I am a dad of 2 daughters, and as a good dad, I like to play games with them, such as Super Top Trumps Harry Potter edition. My youngest is going through a phase at the moment. Fine, but as a nerd, I also want to make sure that I win. So I'm going to use a few bits of maths to make sure that I always win at Super Top Trumps. Super Top Trumps consists of these cards with some statistics on them. All you do is someone says, I am going to choose family tree, and then you'll say what your value is, and then whoever's got the highest is the winner. And then you carry on going. It is a most engrossing game. At least that's what I tell the girls. Not quite in those words. So, how can I tell which is the best stat on here? Well, here's all the stats, which, yes, I literally copied down by hand because that's the sort of thing I do. And I want to find a way to see which stat is the best when compared to all others of that type. You can go with things like, and so to calculate that, first we've got to go into things like mean, median, mode. When people say average, they are being imprecise. There is no one thing called average. Say average to a statistician, and they will say, because that doesn't exactly exist. There's mean, median, mode. When most people say average, they mean mean, which is add them all, and then divide by the number. That's the median is if you put them all in a line in order, which one's in the middle. And mode is which one you got the most of. If you've got a lovely normalized data set, that is kind of like the traditional bell curve, these 3 numbers will tend to agree. Now, what you see here is that the numbers don't really agree, which suggests that we do not have a normalized, nice bell curve-shaped data set, which indeed we do not. More on that later. So to get an idea of how much of an outlier a data point is, we first calculate variance. Now, these are the sorts of algorithms I'm writing in this talk. I'm not going to get bogged down in the specifics of any particular programming language, but this is kind of like a pseudo code to give you an idea. I'm a little pushed for time on this one, so I'm not going to talk through all of these in any sort of great detail, but you can see that this is basically a for each. In C#, like I work in, I'd probably do this as a select statement. You get the idea of how this is done. You can all have a copy of my slides after if you want to have a go with this. It's no problem, but time is short. But a quick bit of ancient Greek for beginners. There are a couple of ancient Greek letters I shall be using. One is sigma. Sigma here is add them all together. That's a dot sum or whatever, or dot total, whatever your programming language calls it. And mu there, the one that looks like a U with a little tail on it, that means the mean. That is add them all up and then divide by the number that you've got. Mean, average. And you get the idea. I'm using mu there as a variable, almost like it's a function, and just saying, take the average of the number set when I say stuff like that. It gives you the variance, which in and of itself is not terribly useful yet, but then what you do is square root it, and what you've got is the standard deviation. The standard deviation, if it's a normalized data set, would mean that from mean plus or minus one standard deviation in any direction, and you've got most of the data captured there. So to find out how much of an outlier it is, you work out how many standard deviations from the mean it is, and that gives you an idea of how much of an outlier you've got. So if you're trying to win at Super Top Trump's Harry Potter edition, what I would do is calculate the standard deviation, which clearly I'll be able to do in my head or something while I'm playing with the girls, and then the more standard deviations above mean it is, the more likely it is that you've got yourself a good one. There. How to beat your kids at games. Right, so this is what the data looks like. And yes, indeed, they are not terribly normal formed. This is basically like a consequence of it being Harry Potter edition. First year, they're massively skewed towards more recent, that is first year at Hogwarts, because, of course, most of the characters are the kids who started all in that very same year. I think it's like 1990-something or other. See, wand length, there we go. Looks like shorter length wands are in vogue. And family tree, you either have hardly any family or flipping tons. The flipping tons over there is literally the Weasley family, by the way. That's literally just them. The one random outlier in first year, that is Dumbledore, because apparently he started in like the 1800s or something. Wow. So you can work out how much as well these things correlate to each other. And here's the formula for doing it. Correlation is, to what extent does data property 1 and data property 2 correspond with each other? The value that you get back from this formula is a decimal value between 1 and -1. 1 would indicate perfect synchronicity between the two data points. -1, perfect inverse synchronicity. That is, as one doubles, the other halves. 0 would indicate absolutely no connection at all. They have nothing to do with each other. Low values close to 0, probably coincidence. But this is the sort of thing you play around with, as I have. So can we see any strong correlations? This is using something, this is a Python library that you can use to generate this, by the way. And yes, wand length has a -40% correlation, that is an inverse correlation, with first year, which tends to suggest that maybe shorter ones have become a fashion, and previously it was longer ones. I don't know. I got nothing to say here. And 43%, that's ones, that's one length to Top Trump's rating. Oh, 40%. So having a better wand tends to mean that you're better. Again, I'm not touching that. So you get the idea. You got a little bit of an idea of what correlates with what. So that's interesting. But let's try and use this on a slightly more interesting data set. Let's talk Pokemon, because I am not particularly a fan of Pokemon, although I do enjoy Pokemon Go. And it's as good as anything. So I found myself on Kaggle a data set of all the Pokemons. I think that's how you say that. So I popped this into my correlation, and we can see there are a whole load of interesting correlations. I'm not going to go into all of these. Just about the strongest one is between weight and height. It's a 63% correlation, which is pretty good. So we can, in fact, do something to try and connect the one to the other. And that's what the graph looks like. If you pop it in a scatter chart, weight to height, great. So let's talk about linear regression. Linear regression is working out a formula that will go from one data point type to another. That is, go from height to weight or weight to height. You know the one, therefore you know the other-ish. It's an approximation. That's the whole point of this. It's not going to give you an exact, proper, literal value. It will give you an approximation based on all the existing data. But at least it's something. And depending on how correlating your data is, depends on what results you get at the end. But this is part of the formula. You need x, y, x squared, and y squared. X and y here are the two data sets. So x, for example, is going to be height. Y is going to be weight. Think of those as columns in a spreadsheet. And then you plug all of that into these dirty great formulas here. And what you get at the end is a simple line equation. Y is equal to intercept plus gradient multiplied by x. Simple as that. And once you've calculated this, it's incredibly efficient to use this as many times as you like because it's a simple linear equation. So sorted. And I've run this, by the way. I actually did this in Excel because it turns out that Excel is one of the best machine learning tools known to exist, and I'm as surprised as you are. And there we go. The weight of a Pokemon is equal to minus 12.5, roughly, plus 63.5 multiplied by its height, which suggests that for every meter of height, it gains about 63 kilos of weight. And if you could get a hypothetical zero-height Pokemon, it would have a negative weight somehow, but fine. That's actually never going to happen, so I'm guessing that's why that doesn't matter. And that's it. That's as simple as it gets. And if I plot this equation line against the data set, you can see that it's kind of loosely following the central path of that scatter. Of course, this is all Pokemons. This is not like where you'd get a really high accuracy on this would if you sat there playing Pokemon Go for about a week, writing down the weight of every single Eevee you met. Yeah, we'd get a really good correlation and basically we'd nail it. But this is all Pokemons and they're all made of different things, like some of them are literally made of steel and all sorts of other weird and wonderful things. So you're not going to get that great a correlation. But still, in principle, though, that's a pretty good a demonstration. You can also calculate the error. The error is how wrong are we? How much did what we made, the equation that we made, how accurate was it compared when you compare real data to prediction? And this is how you do it. You add together, there's the add them all together one, you add it, and you do various bits where you're deducting from the mean and the calculated value, stick it all together, and you get something called R squared, and that gets you your error. So in my case, R squared, that's the error, is equal to 39.7. So it's not brilliant. I'd love something much higher percentage, but rather, it's not the amount of error, I should say. It's actually the percentage that represents how good a fit it is, how right was it. So the higher it is, the better we are. What we really want is a super high value. We don't have one, but fine. That's all right. It's just a demonstration. It's all very silly. If you want to see, though, a bit of data that has a very high correlation, I popped this off the internet, various numbers based on years. And there we go, popped it into an Excel spreadsheet, did my correlation check. It's 96% correlation. That's really, really, really high. That's a fantastic correlation. There it is on a chart, so you can see it pretty much is following a linear path already. So I worked out my bits and pieces, got my gradient, intercept, made my equation. There it is. And then I mapped my equation based on actual data, and you can see it mapped pretty closely. Error, 96.4%. That is pretty much a match, statistically, this is. Now, what is this data? It is the profits of Google versus the sales of cheese in America. Who knew? People in America need to start buying less cheese. What are you doing to the world? Although I do like cheese. So what I'm trying to point out is that correlation does not mean that there's a meaningful relationship between these things, and you have to be aware of that. Putting together a decent machine learning system of any sort involves understanding your data and the meaning of the data. Just finding correlations in and of itself is not enough. Otherwise, you'll end up with nonsense like this. There is also the famous one of, isn't it something like there's an inverse relationship between the average global temperature and the number of pirates in the world. Therefore, more pirates. It's not working that way. Wish it did. Okay, multiple linear regression. What if we wanted to do a whole load of stuff? First, I need to talk about matrices, the matrix. This is a wonderful example of a film that just thought that sounded cool and used it as a title. I refer you also to Source Code, which has no source code in it. It's the name of a computer program for some reason. That must have been confusing during dev. Look at the source code for source code. Fine. Matrix, it's just a way of taking two grids and multiplying them together to make a new grid. There you go. So if you want to work out that top left one there, then that is equal to basically take each item in the rows from the first one, the columns from the other one, multiply each set together and stick them all together, and there you've got a new matrix based on the number of rows of the first matrix and the number of columns of the second. And the order is important. If you change the order of those two, you will get a different shape and value of matrix at the end. I also like saying the word matrix because of that film. Okay, and that's what our multiplied matrix ends up looking like at the end. Turns out, once again, Excel, it's actually literally got a whole load of built-in functions for doing exactly this stuff. Who knew? Excel. It has its uses. Matrix multiplication. Transpose means take a matrix that's like this, turn it to like this. And M inverse is kind of, don't even ask. I looked into what that was all about. It's the matrix equivalent of turning X into 1 over X. Don't bother looking into the maths of it all. It is so mind-bogglingly complicated, it will just hurt your head. Unless you're really interested, in which case enjoy yourself. Okay, so how do I go about making an equation, a linear equation, using multiple data sets, not just one? I'm going to use 3 in my instance, because what I'm going to do is I am going to calculate, that's weight, yep, so that's weight based on height, the number of steps required to hatch an egg, and the defense value, because apparently those will correlate pretty closely with weight. There's probably some sort of meaning to that, or not, I don't know. But here is what you do. Take that great big matrix with the columns based on X, do a transpose, do a matrix multiply with the original, do an inverse, do a multiply with the original again, and multiply, and bang. Basically, it's a several-stage step. I'm not going to go through all of these at the moment because I'm short of time, but you feel free to have a look at this yourself. But basically do about 4 matrix operations, and then what you end up with is a simple little matrix which contains the intercept and each of the gradients. It is actually a lot simpler than it looks, as long as you've got yourself a matrix multiplication formula to do all that for you, in which case it's horribly complicated. So, Excel. Okay, what that means is that my equation using these data is the weight of a Pokemon is minus 70.5 plus height multiplied by 48.5 plus number of steps required to hatch an egg multiplied by 0.003, the number of hit points multiplied by 0.7, put all that together, and then you've gotten yourself an error rate, a new updated, of 47.26. When you compare that against previous, that's actually an improvement. So we're getting closer to being able to do an accurate thing. I mean, you're never really going to get that close when the data is so utterly distributed all over the place, but it's still pretty good. So let's use that same principle, but now to do logistic regression. So linear regression assumes that you are mapping from one set of values, one range of values, one kind of data type, into another data type, both of which are continuous. Logistic regression assumes that you are coming from a set of linear values into effectively a Boolean. True or false? That's what that's all about. True or false? What's the probability that a label is true or not? So I am going to look at can I calculate whether a Pokemon is a legendary, which is just an arbitrary label that's applied to particularly big and stompy Pokemon like this Dialga here, which is not applied to a little Pikachu like that. I'm guessing this fight probably won't last very long if we were to actually let this animation run. Not that it is, although I would watch that. So going back onto here, let's see where are our strong correlations with is it a legendary or not. There we go. Our strong correlations, as it happens, are base egg steps. That is, how many steps before it lays an egg. That makes sense because you don't want your legendaries multiplying too much because that would outbalance the game. We've got a negative correlation against happiness. Oh, turns out the legendaries are how sad. Oh, Pokemons. And a negative correlation of 33% against capture rate. That makes sense. They're hard to catch. And that's mostly about it. Oh, weight. They tend to be heavier. Speed. There's also, speed there. They tend to be faster. There's a few others. So I captured the ones I thought were the best. Ran it in through the multiple regression thing in Excel. And what I get is this. So there's all sorts of gradients there. There's 1, 2, 3, 4, 5 gradients that I've calculated, plus my intercept. And then what you do is you use the exponent function to say the exponent of that divided by 1 minus the exponent, and then that actually gives you your probability rather than a predicted value. Because trying to predict make a predicted value in... Look, gone down there. Why is that? Ooh, what's gone on there? Okay. I don't know why that's disappeared down the bottom, but as it happens, oh yes, exponent, it's a great big number. It's x raised to the power 2.718, blah, 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 blah. It's a big old number. So that means if I wanted to do my calculation, it would look something like this. The left column is the actual values. It has to be numeric, and I've used 0 and 1 to represent Booleans. And then we do our is legendary multiple regression. Of course, the value there is meaningless because it can only be 0 or 1. Anything else is irrelevant. So those don't really mean a lot necessarily. Switch over to the next one using the exponent formula, and then you've got an actual probability. And then within that probability, you can make a choice on where's your boundary. You can set it at 0.5. That would be a good place to start. But it might turn out that you get better results if you put up your boundary to 0.6, 0.7. I believe I used 0.7 in my calculation to decide that was the cutoff point at which I'm certain enough that this is a legendary to say true in my prediction. And this is what I get. So the green there is true negative. That is, I thought it was false, I got it right. The orange is true positive. That is, I thought it was true, and it was true, I got it right. The incorrect ones are that little sliver of yellow there. It's basically 98.88% accurate. That's really good. And it happens that it does help that there are actual correlations at work with our legendaries, so yeah, I'm happy with that. That's pretty good. Naive Bayes. Now, I'm a big fan of Doctor Who, as nearly anyone that's met me for more than approximately 4 minutes will know. I will talk about it at length without stopping, do be warned. So I decided to make a Doctor Who example of what's a naive Bayes classifier. These things are actually incredibly important. They get used in all sorts of places, including things like spam filters and stuff like that. It's a way of determining whether something is true based on its properties and whether it's likely that this shares properties with existing examples of that. There's all sorts of ways to use it. So let's have a look. There have been an awful lot of this is now out of date. Poor old Shooty Gatwa had only got one story when I wrote this. He's now got 10, I think. So you're just going to have to accept that the numbers are a little bit out of date, but that's fine. So what I've gone with is there's been an awful lot of Doctors, and each of them have had a different number of stories, and then underneath that, they did occasionally meet the Daleks, who are the most popular baddies in the whole of Doctor Who history. And I wrote underneath it, how many times did those Doctors meet the Daleks in one of their stories? And then from that, we get a probability of what's the chances that the Daleks turned up based on, we got a random bag of Peter Capaldi stories, I pulled one out, was it Daleks? And that's the probability under there. What I'm going to do with naive Bayes is flip this on its head. Okay. That's the formula. The probability of A given B is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. That's all very well and good, but what does that get us? There we go. What it means is I already have the probability of Daleks given Doctor. So given William Hartnell, the probability of Daleks. Using this formula, you can change it to, rather than it being a bag for each Doctor of Doctor stories, now we've turned the whole thing on its head and you've got yourself a bag of all Dalek stories. And given a Dalek story, what's the probability that it's a given Doctor? That's what that formula does. And that is, if you want to see a slightly more interesting way of using this, I made a classifier that will tell you whether a random sentence from one of these two books came from one book or the other. I used public domain because I do not wish to get sued, plus these are two of my favourite books of all time. Journey to the Centre of the Earth by Jules Verne and The War of the Worlds by H.G. Wells. Now, I didn't make it too easy for myself. I used an English translation of Journey to the Centre of the Earth. Otherwise, that would have been really quite easy. So, given a random sentence from one of these books, can I make a classifier that will tell me which it is with a decent degree of accuracy? Well, yeah, of course I do. How did I do it? Get all the lines. in all the book. Remove the stop words. That is, I got this off the internet somewhere, stop words. They are really common words that tell me nearly nothing. Words like you, yours, she, hers, their. Tells me nothing. Take it out. It's just noise. Okay. Remove little one-word lines, because they tell me nothing as well. And remove numerical words. That is, take numbers out, because numbers, once again, tells me nothing very interesting. And then that means I've sort of, the rather famous opening of War of the Worlds gets shortened to one would believed last year's 19th century. Those are all words that are pretty easy to look. They're uncommon, and so they're going to give me better probabilistic results compared to little words like a and, the, and should, and so on. Okay. And here is my first calculation. I don't know if I'm blocking it over here, but you take the word one, run the probability of the word given that it's War of the Worlds, get the probability of the word given journey to the center of the earth. So the probability of the word is equal to the two added together. And then we can put this into another formula, which is the probability of the word given journey is equal to the, and so on. There is my formula using naive Bayes, which again, you can look up if you want to copy my slides. But that gives me a probability that this word appeared in journey to the center of the earth at being 22%. And the probability it's in War of the Worlds is, it's 1%. Wow, okay. But fine. Oh, sorry. But that's just one word. That's one word. But the point is, I'm going to go and apply this to each word in turn. And each word I add will make this a little bit more accurate every time we do it, because you just take the prior probability. For the first one, we assume that the probability is 50-50 between the two, because we need the probability of the word occurring at all in either book. And then each time you add a word in there, you update that probability that the word will occur at all in either book and shift it based on the results of the previous. And then bit by bit, you get yourself a slowly more accurate result. And what you see here is, initially, the probability that this sentence, it is War of the Worlds as it happens, initially jumps up to War of the Worlds with a high percentage. And then as it goes on, we get a slightly more accurate result as it jumps back and forth for a little bit. And then eventually, War of the Worlds is consistently on the top. So the more data you feed in, the more accurate your result's going to be. Now, in spam filters, they'll probably use all sorts of things like common words. They'll probably use things like address. There'll be all sorts of data items you can use. And given those, you can do the same naive Bayes thing by taking as many old actual spam messages as possible and then working out probabilities from them. And then you get yourself a reasonably accurate spam filter that can decide whether this belongs to a category or not. That's the point of it. Okay, nearest neighbor. Right, this one's a simple one. So this is for working out, based on numeric data, where does a new data item fit in compared to all the old ones. So you calculate the Euclidean distance for all data. I just like saying Euclidean. That's just your basic, Pythagoras thing. Work out the hypotenuse, straight line. That's pretty much Euclidean. Order it by, so do that for every single data point. Order it by distance ascending, that is the nearest one, the smallest distance at the front, and the largest distance at the back, and then pick the top however many. K is however many you want. Play around with that until you find a value that works best for you. I think I picked 5 in my case. And then whichever category those most commonly appeared in is the one that you choose. So this works for some kinds of data and not for others. For my example, I chose color. So there are 3 axes in color, red, green, and blue. So then I decided that I'd get myself a data set of colors so that I could get some Euclidean distances. I generated a random color. So what I want to do is work out which color this is. And these data points are all categorized by which shade of what they are. So this first set is all grays, and then there's a set of all reds, and so on. So what I'm going to do is work out which colors are closest based on Euclidean distance to this new one, and then that will tell me what it is. Now, if I had to guess, I would say red, but who knows? So calculate your distance, which is your basic Pythagoras thing. Do that for every single. So for example, the first color out of there is a gray, 84, 84, 84. Do my basic Pythagoras thing, work out the Euclidean distance, which is 143.7. The actual value there doesn't matter just so much as how does it compare to all the others. And then do that for every single one. And actually the closest are these ones. Turns out it's brown. Okay. Fire brick brown, brown, brown. It's brown. Okay, fine. But you get the idea. I have seen people do things like use it on mapping data where they've got data points that say sea or land, and then you can use it to determine whether an arbitrary point is in the sea or the land based on what's nearest to this. If it's mostly sea, then you'll say sea. If you take 5 and there's like 3 seas and 2 lands, well, that's probably a sea, and so on. So you can take, again, a sort of a fuzzy idea and try and turn it into something a little bit more solid. You won't always get it right, but it will probably give you something close enough. How are we doing for time? Yeah, okay. Right, last one before we wrap up. I'm just blasting through this. So decision trees. This is probably the most common form of machine learning you'll see out there. Now, I'm going to warn you, the maths behind this are ridiculous. I mean, really ridiculous. They're so complicated. This had to be an entire talk by itself if you really want to go into decision trees. So I'm just going to give you an idea of how they work. And really, honestly, I would just let the computer calculate them because the computer's better at this stuff than we are. So I'm going to use a demonstration using, once again, a kid's board game. I don't know, was this board game ever a thing in the Netherlands? I don't know. This is Guess Who. Once again, I want to make sure I beat my kids at this game. This is the specific edition that I always used to play with my brother when I was little, and I want to find out how I can make sure that I win. So the way to win, actually, in Guess Who, is to ask a question that eliminates 50% of whoever's left. Because whether the person on the other side says yes or no, you lose 50%. That means you don't get any fantastic low probability hits, like you said, are they wearing a green hat? Yes. Oh, I win. Because the chances of that working are low. So most of the time, it's not a good strategy. Best strategy long term, 50% of the people. So are there any, there are stats that we can call on that gives us about our 50%. How many are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 by 3. Oh, 8 by 3. Anybody? I'm terrible. Sorry? 16, 24. No? Yeah, good. I'm terrible at mental arithmetic. Good at maths, terrible at arithmetic. So, 24. Hair color. No. Best we got is 5. No, that won't do. Gender. No. It's completely gender biased, this game. Now, I would read very little into that. It probably says less about the attitudes of the time and more about trying to make a game that's not too unbalanced, because if it was 50-50 like the real world is, then basically everyone would always start on that question. What about things like facial hair, eye color, a big nose? I tried all sorts of things. Could not find a single statistic that would actually give me my 50% removal. So what did I do was compound several characteristics and say, does your person have a hat or glasses or jewelry or earrings or a bow? Now, this is very likely to get your opponent to take their board and throw it clear at your head. But by God, you'll win. So with that first one, if they say, yes, it's 11 people that I've got left, otherwise 13, that's basically as near to 50-50 as I can get. Female or facial hair. Yeah, once again, pretty good. I couldn't find any literal 50-50s. If anyone ever finds one, tell me. And hat or glasses or blue eyes. I was quite proud of finding that one. So, yeah. This is how you do it. Work out how to split your data set into a 50-50 choice. So my question number 1, let's start playing our game. Female or facial hair? And it is, yeah, oh, I skipped. Yeah, oh, okay. Yeah, and what are those numbers meaning? Oh, okay, that's how many we eliminate. Female or facial hair? Yeah, it was. So that leaves us with these guys all eliminated, because that was a yes. Either female or facial hair. Bang. Okay, we're already a good chunk towards winning the game. Next question. beard or blue eyes, which was based on the remaining people, the best way I could find of separating these out. I didn't use this, it's not the same set of questions I'm using again and again. Based on whatever the previous answer was, I'm then formulating a new set of questions based on the data that's remaining to separate that into two partitions of roughly equal size. Beard or blue eyes, is it a yes or a no? It's a no. So now we've eliminated 7 people more. Great. So take those remaining people, 1, 2, 3, 4, 5, 6, 7, and what's the best way now to eliminate half of them? Black hair. Yes or no? It's a no. That means we've got 4 people left. Okay, based on these remaining, I think it's 4 people. Yep, 4 people. There we go. We've got Susan, Maria, Charles, and Claire. Notice that it is getting close to being only women, even though I've never actually asked a question about gender. That's sort of naturally sorting itself, because, spoiler, that's kind of going to be one of the right answers. So let's go with hat. 2 of those people are wearing a hat. Is it a hat? It's a hat. That leaves us with just 2. It's only women. It's Claire or Maria. Who is it going to be? Well, to be honest, at this point, we can just ask, is it Claire or is it Maria? And those will do, because either way, we're eliminating someone. So, is it Maria? It's Maria. My personal favorite. I loved her. I missed her. She's not in the new one anymore. I'm very sad about that. If anyone knows where she's gone, let me know. I hope she's all right. Right. That will do for our equations. If anyone wants to do any further reading, there is this really most excellent book. This is not a machine learning book. This is a statistics one, but it's really good. It makes a very good effort at trying to make all of these rather complicated things a bit simpler, and statistics underpins all machine learning. To understand properly machine learning, you necessarily have to understand statistics. So I would start here. I've also been recommended this book, which is available for free online, free being my favorite price of all of them. So have a look at greenteapress.com/thinkstats. This is a very good book, also available for free online, although I do own a physical copy because that's the sort of bedtime reading I take to bed. The 100-page machine learning book, which is an awful lot of... It's fairly dense, and it doesn't necessarily contain all of the theory you might like to understand every concept, but it's a good starting point to understand what all you need to know, and then you can take it further from here. So, oh my goodness, I'm going to give this a go. Eingarti Punthanaton Aite Ermenuton. How was that? Probably no one knows. But does anyone have any questions? No? Okie dokie. If anyone wants further information beyond that, okay, this is my GitHub, where you can find copies of some of the source code I used, although a lot of it was you'll find in Excel, so I didn't necessarily put it up. But there we go. That is my GitHub. This is my blog, where you might find some articles that go into more detail about these and contain a lot more working. So if you want to go through some of these, there is a multi-part series I wrote on some of these ideas. This again is my book, which is, as I warned you, really quite silly. As well as telling you all about functional programming, you will also find out who is my favorite James Bond and who ordered the pizza. You'll know it when you find it. And this will answer any remaining questions. So I will thank you very much.